So, in this video, you will learn how to rationalize the denominator. Okay, when you say or rationalizing the denominator, it means that you're simplifying the radical expression in such a way that you are not allowing a radical in the denominator. So, a radical expression is considered simplified if there are no radical symbols in the denominator. And how do we remove the radical symbol in the denominator? How do we remove square root here? So let's take for example here 1 over square root of a. Now there's a special case in the laws of surds wherein when you multiply something that is equal to itself, it will give you a whole number. And that's why we can actually multiply square root of a, because when you multiply square root of a, that will give you square root of a squared. And you know that the square root of a squared, that will give you a. But the question, if you're just going to multiply the denominator by itself and get you a number in the end which has no radical symbol, will this value 1 over a be equal to the original? Of course, it will not be equal to the original because you're multiplying something that is different here. When can a value be equal to itself? What number will you multiply wherein when you multiply, it will just still give you the same value of the number or a constant. So that will be the multiplicative identity, which is 1. Okay, and in order to multiply this by 1, what will you multiply to 1 over square root of a, or what expression that is equal to 1 that can actually eliminate the radical symbol in the denominator? In order for this to be equal to 1, we have to have the expression square root of a over square root of a. In this way, you're actually multiplying this term by just equal to 1, and it will not change the value of the original expression. So therefore, if you're going to multiply this, that will be square root of a. So the square root of a over square root of a squared, and we can actually cancel out 2 and square root because square root of a squared is just a, and then therefore we have square root of a. It's okay to have a square root in the numerator. Our concern here is to make sure that the denominator is free from radicals or surds. Okay, this is how you rationalize the denominator. Now let's apply this idea with real numbers. Okay, in this case we have 3 over square root of 2. So just remember, we have to multiply 1 in order for the original expression to be equal to itself. Okay, what expression should I multiply to this whole thing which is equal to 1 but can actually rationalize the denominator? And in order to rationalize the denominator, you just have to multiply it by itself. So square root of 2. And to make it equal to 1, you multiply it by square root of 2 over 2. When you do that, you cannot, of course, you cannot multiply 3 and 2, but you can actually combine them as 3 square root of 2. All over, when you do this, that will give you square root of 4. So why are we actually doing this? Is actually transforming the denominator into perfect square. Okay? So that will give you 3 square root of 2 all over the square root of 4 is just 2. And you cannot cancel out 2 and 2 here because this is a surd and this is a constant. Okay? So just similar to the idea that you cannot multiply the number inside the radical symbol with a constant. Okay, so therefore the final answer is 3 square root of 2 all over 2. Let's have the second example. In the second example, since we have a quotient of 1/5 under the radical, we can actually use the second law of surds here by expressing them into different radicals. And you know that the square root of 1 is 1 all over square root of 5. So the square root of 1/5 is similar to 1 over square root of 5. And how do you rationalize? We have to find a value that can make 5 a perfect square. And in order to do that, we just have to multiply it by itself. Of course, we have to multiply 1, and this is equivalent to 1. So that will give you 1 times square root of 5, that is equal to square root of 5 all over square root of 25. and the square root of 25 is equal to 5. So your final answer is square root of 5 all over 5. And you have rationalized the denominator. We have another example in rationalizing denominator. And in this case, we have 3 over square root of 12. Okay, in this one, you just have to think what can make the denominator rationalize or can be a perfect square. You can actually multiply this by square root of 12. That's an easy way to do it, by multiplying the denominator by itself. So when you do that, you can actually have 3 square root of 12 all over square root of 12 squared. Okay, you don't have to multiply them because you know that when you do this, you can cancel out 2 and squared. So that will give you 3 square root of 12 all over 12. So what we can do here is to further simplify square root of 12, which can be expressed as 4 times 3 all over 12. And the square root of 4 is 2 times square root of 3 all over 12. Okay? So you see, we will not stop unless the number in under the radical is still factorable and has a perfect square factor. So in this case, we can have 6 square root of 3 all over 12. And we can simplify this further because 6 divided by 12 is 1/2. So that will be square root of 3 all over 2. So this is your final answer. Sometimes we can actually multiply this expression not by itself, but of course, the one that can make this a perfect square. That will be good if you can simplify this first. So when you simplify this, that will be 3 all over square root of 12 is 4 times 3. You can actually have 3 all over square root of 4 is 2 times square root of 3. And this is the time when you have to multiply it by the number that can rationalize the denominator. And your concern here is the radical, so you don't have to worry about the constant. So all you have to do is to have 3 times square root of 3, 3 square root of 3 all over 2 times square root of 9. So that will give you 3 square root of 3 all over 2 times 3. Okay, because square root of 9 is equal to 3. So you can cancel out 3. That will give you square root of 3 all over 2, which is similar to the first answer that we got. Okay, this is another way. We can also have another way. Okay, this is a third way. By multiplying this by the number that can make 12 a perfect square. And what's the closest perfect square to 12? Or what do you think you will multiply to 12 to make it a perfect square? You can multiply it by 2 to make it 24, but 24 is not a perfect square. When you multiply it to 3, 12 times 3 becomes 36, and 36 is a perfect square. So that means we can actually multiply 3 times square root of 3 all over 12 times 3 is 36. And when you do that, you can have 3 square root of 3 all over square root of 36 will give you 6. And you can simplify this further. Cancel out. That will be 1. That will be 2. So square root of 3 all over 2. Okay, so I have shown you 3 different methods for this problem. So you just have to choose which method suits your way of understanding. Okay, in number 4, all you have to do is to focus on the denominator. And the denominator is square root of 10 over x. The usual way, we can always multiply this by the variable or by itself. Okay, just remember that whatever you multiply to the denominator, you will also do the same thing in the numerator to maintain the value. So, in this case, we can multiply 5y times square root of 10. Of course, we cannot combine them, but we can actually write them as factors. All over, when you do this, that will be the square root of 10 times 10 is 100. And we always include the variable, because variable can also represent an algebraic expression or just a number. Okay, so that means that will give you 5y square root of 10x. You cannot simplify it further. Now, when you do this, square root of 100 is 10, and square root of x squared is just x. Okay? You can simplify it further by simplifying the number 5 and 10. And the final answer is just y square root of 10x all over 2x rather. Okay? So your final answer is y square root of 10x all over 2x. So I'm including variables so that you will get used to the idea of algebraic expressions. Okay? So see you in the next video. Bye.